Okay guys, so today, Objective 1, we're going to get started with our probability unit. So Objective 1 today is going to be to find experimental probability. This is the very intro topic to the different probabilities that we will be finding. So first, let's go ahead and define probability. Probability measures how likely it is for an event to occur. What is the chance that something's going to happen, or someone's going to do something, or for example, what is the possibility or the chance that Mike Dillanaire will run a state record time at his next track meet? We can take his past runs and his past times and compute different kinds of probabilities to talk about that. And we express probabilities in two different ways. We can either talk about them as a percent, or we can talk about them as a real number. So when we typically see a probability, we either see it with a percent sign or as a ratio, in other words, a decimal. Something less than 1, or if we had 100%, that would be 1. And we can look at that right here. So 0% or 0 is going to be on one end of our scale, and that's the probability. That's going to be the probability of an impossible event. Probability of an impossible event. And then 100% or 1, which is the other end of our scale, is going to represent the probability of a certain event. And that event must happen. In order for us to have a percent of 0 or a percent of 100% or a probability of 1, we would have to have an event that is absolutely for sure 110% going to happen. Okay? I'll give you just a second to get those written down. All right. So if you need a little more time, just ask the sub to pause the video, but I'll go ahead and move on now. And so for experimental probability, we talk about each observation. Each observation is actually going to be an experiment or a trial. So in experimental probability, we calculate the probability of an event. We can talk about this as P of event. That's how we notate the probability of an event happening. Just one second. This is being a little finicky today. There we go. So the probability of an event happening we notate as P of whatever that event. So maybe it's the probability that I use a red pen. So probability of, maybe I would write the word red. Or maybe it's the probability of a pregnant woman having a girl versus a boy. We'd go probability of boy, probability of girl. P of boy, P of girl. And then when we talk about this experimental probability, we calculate this by calculating the number of times the event occurs, divided by the number of trials. Divided by the number of trials. And that's our experimental probability. And again, if you need a little more time to write this down, go ahead and ask the sub to stop the video, but I'll go ahead and move on. So, for example, let's look at this word problem. When the University of Texas won college football's national championship in the 2006 Rose Bowl game, its quarterback completed 30 of 40 passes. Find the experimental probability of the quarterback completing a pass. Now, just for a second, forget that I asked you to find experimental probability. What do you think you're going to do here? We're looking at a quarterback completing 30 out of 40. When you hear the word of here, you automatically are thinking division. You're thinking 30 out of 40. 30 divided by 40, which is exactly what we're doing when we compute experimental probability. We have actual experimental data. This particular trial, this particular experiment, we've got 30 actual times the event occurred, which was completing the pass, out of a total 40 trials, 40 passes that he tried. So our probability of completion here is going to be 40 30, which is our number of times the event occurred, which the event, this is a 0, and I'm going to have to redo that because that looks gross. Here we go. 30% completion out of 40 total trials, out of 40 passes. So we take 30 divided by 40 and we go ahead and simplify that, and what do we get? What do we get? Sure, this is either, we could write this as 3 over 4. That's a simplified version in a fraction. But I told you that experimental probability needs to be expressed as either a percent or a decimal. And so the percent version of this, 3 out of 4, you all know that that's 75%, right? So we can either write it as 75%, or the decimal form of that would be 0.75. Okay, so let's try another one. At the same game, the University of Southern California quarterback completed 29 of 40 passes. Find the experimental probability of this player completing a pass. So take a minute now, go ahead and calculate that out. And so on the top of this fraction, you should have written 29, because that's the number of times the event occurred. Completing the pass actually occurred 29 times. And our number of trials is going to be 40. He tried 40 times to pass the ball for a successful completion. He only completed it 29 times, but he tried 40 times. So 29 divided by 40 gives us a decimal of 0.725. So we can either express our probability as 0.725, or we can rewrite that as a percent. And to rewrite as a percent, all we do is move our decimal place 2 spaces, because we multiply by 100, and we get 72.5%. And that's our experimental probability. Okay? All right, let's go ahead and move on to theoretical probability. If you need the stuff to stop the video and go back, that's fine. Take a minute. So theoretical probability. So let's talk about a dice for a second. When you roll a dice, the possible outcomes on a dice, on a regular dice, are 6. You have 6 possible outcomes. 1, 2, 3, 4, 5, or 6. Just one dice, or one die. So we call this set of possible outcomes, this set right here, this set of 1, 2, 3, 4, 5, and 6, we call this set the sample space. And we can calculate what is called theoretical probability. We can calculate that as a ratio of the outcomes in our sample space. We can calculate that as a ratio of the outcomes in our sample space. And so I'm going to go ahead and go to the next slide. So if you want to pause it and give them a second to write this stuff down, that's fine. So I'll go ahead and move on. So if we talk about theoretical probability, here's your definition. If a sample space has n equally likely outcomes, and an event A occurs in m of these outcomes, then the theoretical probability of event A is the probability of m over n. The event happening, this chunk out of this entire option space, out of all of our choices, what's the probability that this will happen within there? Okay, and this is a little abstract for us right now, but we'll go ahead and apply it here in just 2 seconds. I'll give you a second to write down the definition. Okay, so if we move on to the next slide, then if I asked you to find the theoretical probability of getting an even number when you roll a number die, or a number cube, or a dice, okay? If I asked you to find the theoretical probability of getting an even number, first of all, what even numbers do we have to choose from? Well, on a dice, we have 1, 2, 3, 4, 5, and 6. 1, 3, and 5 are odd, so 2, 4, and 6 are even. And so we have three outcomes that could possibly result in our event, which is getting an even number. So this even number here, this is our event. So we're actually looking for here the probability of getting an even number. So we write that P of even. And our probability is going to be sorry, that was the bell ringing, obviously. So our probability is going to be the probability that we have an event A, which is up here, so three actual possible outcomes out of our 6 equally likely outcomes. It is equally likely that we get a 1, 2, 3, 4, 5, or 6 on this dice, assuming it's not a weighted dice, right? And we're not living in Ocean's 11 or something. So out of 6 total, we have 3 possible ways to get an even number. So 3 out of 6, we could rewrite that as 1 out of 2, 1/2. 3 out of 6 is 1/2. And so we have a probability of, either 0.5, or we could rewrite that as a percent as 50%. All right. So now go ahead and find the theoretical probability of getting a prime number when you roll a number cube or a dice. What's the theoretical probability of getting a prime number? This is going to require you to think about what a prime number is. So take a minute, talk amongst yourselves, see if you can remember what a prime number is. Okay, so for those of you that don't remember what a prime number is, prime number is a number larger than 1, like maybe 5 or 13, that's divisible only by itself or 1. So our prime numbers go 1, 2, 3, because those numbers are all only divisible by themselves, and 1. Is 4 prime? Think about it. No, 4 is not prime because 4 is divisible by 4 and 1, but it's also divisible by 2. Makes it not prime. 5 is prime. Is 6 prime? Nope, 6 is not prime because we can divide 6 by 6, 1, but also 2 and 3. Okay? 7. 7 is divisible only by 7 and 1, so 7 is prime. Well, we only care about 1 through 6. So tally up again which ones are prime. So we've got 1, let's see, 1 is prime, 2 is prime, 3 is prime. We decided 4 is not prime, right? 4 is not prime. 5 is prime. 6 is not prime, we decided. Okay. So our probability of getting a prime number is 1, 2, 3, or 5. So we've got 4 possible outcomes of the event, and then out of a total equally likely number outcomes, 6 total choices on the dice. So out of our 6 total choices, we've got 4 out of 6, which gives us a simplified fraction of 2 out of 3. So our theoretical probability then is, yeah, sure, when we round this, we get 0.66666, right? So 0.6 repeating. Or we can write this as a percent. This is just 66%, right? Or 66.6 repeating if we wanted to be really, really thorough. Okay. So that's pretty much all I have for you guys today in terms of the objectives. So for homework, the sub is going to pass out right now a worksheet for you. I'd like you to start with the worksheet. And on the worksheet, I want you to do on the reteaching 1 through 6